Hey guys, so quantum machine learning, it's all the rage nowadays. It's the ultimate culmination of buzzwords. So I thought I'd make a video and show you how to code a quantum neural network completely from scratch and run it on a real quantum computer from IBM. So first of all, what is quantum machine learning? Well, it simply means that we want to use a quantum computer to learn from data and to then use it to make predictions on new data. A very popular framework for classical machine learning is neural networks. And in this video, we're gonna build the quantum version of neural networks. As always, for this tutorial, I'll be using Qiskit, IBM's quantum computing module in Python. If you don't know what Qiskit is, I highly recommend you to watch my very first video where I explain how to set everything up. I would also recommend you to watch all previous coding tutorials where I explain the basics of how to write programs for quantum computers. Alright, so we're gonna be starting off our tutorial here in a Jupyter notebook. And so the first thing that we need some data. For machine learning, we need data. So I'm gonna head over here to scikit-learn, which is one of the most popular machine learning modules for Python. And I'm gonna click here on examples and let's see what data we can use today. So I'm scrolling down a little bit and how about we use the iris dataset? So the iris dataset, it consists out of three different types of irises. So the flower iris. And these flowers here, they are basically represented by four numbers. A sepal length, sepal width, petal length, and petal width. So just four numbers. Those four numbers are called features. And with three different irises. And so we're going to be using those four numbers to then classify the irises, so these flowers. So now let's go back to our Jupyter notebook and let's import this data set. All right, so I've now imported here the data. And I've already split it into a training test and into a test set. So we're gonna be training our quantum neural network on the training set. And then afterwards, we're gonna be evaluating its performance on the test set. And I'm using here 1/3 of the data as the test set. And as you can see here, out of those 150 data points, I'm just using 50. Because I will be doing a binary classification. So if you look here at train, then you can see that we have two types of flowers here, and we're going to be classifying the data, so these different lengths. So this is in X train. All right, so these are now the data points, and we have these four numbers, the features. Okay, so now that we have our classical data, we have to figure out how we get these numbers here, these classical numbers, onto the quantum computer. So as a first step, I'm gonna be importing everything that I need from Qiskit, IBM's quantum computing module. In case you don't know what Qiskit is, you can watch my very first video where I explain everything in detail.
Ability to each according to his need. Now we've been told this was a Marxian.
All right, so since we have here four features in our classical data, I'm using 4 qubits. So n, the number of qubits, is 4, and then I've just here basically initialized a quantum circuit. As you can see here, we have 4 qubits and 1 classical register, which is where the result is going to be written to. So the measurement is going to be written there, the classical output. And so to get those numbers onto the quantum circuit, I'm going to do a very simple trick. I'm just going to be rotating the qubits around by these angles. So the first qubit is going to be rotated by this 5.2, the second one by 3.4, so on and so forth. So let me just write this out here. Alright, so as you can see, this rotates the qubits, and this then encodes those classical numbers onto the qubits. So obviously this can be done in more complicated ways. Rotating the qubits is really just the simplest way of getting the data onto the quantum processor. And this process here is called a feature map. So I'm now going to be putting this thing into a function called feature map, such that we can map generally any data onto the quantum processor. Alright, so this is now the feature map. And as you can see, if I change here the data point, it will have different rotations, so it can indeed map the data onto the quantum processor. So now the next step is we need to measure the quantum circuit here. We need to get some output. And the output, so this measurement, is then going to be our prediction of the quantum circuit. So now let me just put here a measurement operator. Okay, so as you can see, now I'm measuring the 0th qubit. And so this output here can be either 0 or 1. Now, basically the idea is that I want to introduce a variational circuit. So I want to introduce some more rotations that we're again gonna be learning. So let me just show you what I mean. Okay, so now I've put here two barriers, so these gray lines for visualization. So essentially, in between those two gray lines, I want to put some more rotations. And those rotations, they will have angles that we want to learn. So we want to optimize those angles such that the quantum circuit then predicts the right label. So the right label in our case would be Y train at 5. So in this case, we would want the quantum circuit to output 0. So now I'm just going to be coding the quantum variational circuit, which goes in between those two gray lines. And I will explain to you how it works. Alright, so now I've put here the variational circuit in between these gray lines, the barriers. And so, as I said before, this variational circuit now contains rotations here, RY, so we're now rotating around different axes. And these rotation angles here, I've now put just random angles for illustration. But the goal is now that we want to learn those angles. We want to learn the optimal angles such that our quantum circuit outputs us the right thing, so the right class. And these other blue lines here, they are C0 gates. So these C0 gates that I've put here, they create entanglement, and so they essentially allow information to travel from one qubit to another. So I'm measuring here the 0th qubit, and so the C0 gates essentially allow the information from all the other qubits to also travel to that qubit, such that I only have to measure one qubit. So now let's just check out what this quantum circuit will currently output. So now I'm just gonna run the quantum circuit and see what output we get.
It's one of those days.
All right, so I've now here run this quantum circuit 10,000 times. So this is here shots. And so I've run it on a quantum simulator, this Quasm simulator, which simulates the quantum computer without any errors. And so I've executed it and I've gotten here the counts. And so out of those 10,000 times, I've gotten 3,606 times 0 as an output and 6,394 times 1. So this means that I've gotten 63% of the time 1. So we could then basically say that the prediction of this quantum circuit is that the input, so here train at 5, is 1 of class 1. But if we check down here, it is actually of class 0. Well, this makes total sense because these angles here, the thetas, we have not trained them yet. They're just random values. So now we could basically put all of this here into a function, into the quantum neural network function. And this is then just basically producing the prediction of our quantum neural network. So let me just put all of this into a function. All right, so now I've put everything into a function, and as you can see, this quantum neural network function, it returns us a prediction. And in this case, the prediction would be class 1, since we're closer to 1 here in the output than to 0. And so that means that our output here is actually wrong. So now let's just call this here prediction, and let's call this here the target. And so how can we compare these two? Because we basically want these two to be equal. We want the quantum neural network to output the target. So we could just write prediction minus target, right? So I just need to execute this cell. Okay, so this here basically subtracts the two. But, well, if we put it in the other way around, so actually if I write here target minus prediction, then this can end up being a negative value. And so if I play around here with a few data points, let's just see, then this varies around. And so just to make sure that this is a positive value, I will just square this here. I will just put a square here. And so now this here basically quantifies us how good our prediction is, because if this here is 0, then our prediction matches the target and we have trained our quantum neural network properly. Now let's just put this idea into a function. I will call this a loss function. All right, so now I've got a loss function. So now the next step is we want to minimize this loss function. So essentially the loss function tells us how close we are to the real target. And so we want to minimize this loss function. So basically what we need to do is we need to loop over our data, and we need to update our variational parameters. So those thetas here in the quantum neural network, such that we minimize the loss function. Okay, so let's just do this now. Let's just write down this general idea. Okay, so this is the general idea here. So we're gonna loop through our training data. And for every training data example, we're gonna get the prediction of our quantum neural network. We will then plug this into our loss function, which tells us how far our prediction is away from the true value. And then we're gonna be using this information to update the thetas, so our variational parameters in the variational circuit here. Now, the way that I'm gonna be updating this is with the so-called stochastic gradient descent rule, and this is a really simple rule. So let me just write it down. Okay, so this is the gradient descent rule. So basically I'm updating the variational parameters theta every time I see a data point example. And I'm doing this by using the gradient here. And the gradient is essentially just taking the derivative of the loss function with respect to every entry in this theta vector here. And this is multiplied with eta, and eta is called the learning rate. And so for our purposes, I'm going to be using 0.05. But this value here varies a lot depending on what data you have. So this is a so-called hyperparameter that you just kind of have to play around with and see what works for the data. So now what remains for us to do is we need to actually put here the gradient function. So now let's just write down the gradient. All right, so this is the gradient. So the gradient, as I was saying before, is just taking the derivative of the loss function with respect to every variational parameter. So the way I'm calculating the derivative is using finite difference. So basically just what you learned the first semester of calculus. And so the finite difference rule is very simple, right? You just evaluate the loss function at theta plus a small value, which is this delta here. Then you subtract the loss function evaluated at theta and you divide it by the small value here. And I'm doing this for every theta value here, which is why I'm looping over this. And then at the end, we return the gradient vector. And so this is all we need here. And so this then basically finishes up our gradient descent update rule. Now, typically you require a few more passes through your data set. So this here would just be one pass through the data set. So now let's just put another loop here to pass a couple of times through the data set. Okay, so this is called a epoch, a training epoch. And so we're gonna be passing through our data 20 times. And so to keep track of our training progress, I'm gonna put here a temporary loss list. So loss temp, and this will be updated by our loss function. Okay, so then basically for every training example, we get a loss function, and then here at the end, I'm just gonna update this loss list here with the average of the loss that we've gotten by passing through the data set once here. And so what we expect to see is that this loss here during our training is going to go down. Now, another thing that is quite interesting to keep track of during our training is the accuracy. And the accuracy basically just tells us how many data points does our quantum neural network classify correctly. So now let me just code here quickly this function. All right, so this accuracy function, it just loops through our data. It gets the prediction for every data point here. And then so if the prediction is less than 0.5, and if the true label is 0, then we increment the counter once. So this means that it's correctly classified a data point. And if it is, the prediction is bigger than 0.5 and the true label is 1, then we also increment the counter by 1. And so then what we return is we return basically just the percentage of how many data points we got correct out of all of the data points that we are showing. So I'm just gonna basically calculate the accuracy here as well to keep track of it during our training. Okay, so now we're almost finished. I've just now put here a print function just to see the progress of our training. And now I just need to initialize our variational parameters. So theta, I'm just gonna be initializing them with ones. And so now let's just check. I think this is all we need. Let's just go up real quick. Actually, looking here at our quantum neural network, we're currently only using a quantum simulator. So let's just add a few more lines such that we can then also run this whole thing on a real quantum computer. And so once we've done this, then we can finally train our quantum neural network. Okay, so if simulator is false, then I am running this on a real quantum computer. So the number of shots I had to reduce here, because on the real quantum computer we have less shots, so we can run it fewer times than on a simulator. And so here at get backend, I have to put the name of the quantum computer. So now let's just check the IBM quantum experience real quick. We'll go here on the left to systems and simulators. And so those are the machines we have available. And since we are using only 4 qubits, I'm going to be choosing one of the 5 qubit machines. And so I can either choose basically the Santiago or the Athens one. Both have a high quantum volume, so they are pretty accurate. So let's just use the IBM Q Athens. I think I haven't used this one before in any tutorial. And so we can see here we have currently 46 jobs in the queue, and we can see the error rate and the layout of the qubits. Okay, so now let's just paste this here into our backend. And so now this allows us to also run the training on a real quantum computer. Okay, so I think we've got now everything that we need, and we can finally run this training here. Alright, so we have now finished our training. As you can see, the loss function has gradually gone down. There are also some bumps in here, but this is totally normal since we're doing stochastic gradient descent and there is some randomness involved here. You can also see that maybe we should have trained it for a bit longer, but let's just keep it as it is. And let's just see what test accuracy we achieve. We can see here in the training accuracy has gone up all the way to 86% at the best point. And so now let's just see what is the accuracy on the test set, which it hasn't seen before. And this is really the most important thing. Okay, so the test accuracy is 75%, so it gets 75% of the data points right. This is not particularly great, but I think we could improve that by training it a bit longer. We could also have a better loss function. We could also have a better variational circuit, and we could also do some normalization on the input data. But let's go into detail. I think this is really good for illustration of how to do quantum machine learning. Now let's just quickly compare here with a classical method to see kind of what our competition is and how good our competition is. So this is just a classical machine learning model, and I'm just gonna see how accurate this is. So I'm comparing here the prediction of that classical model with the actual target, and you can see we're pretty much getting all of them right. So yeah, the classical alternative is very fast and it is very accurate. So yeah, we've got a bit of room for improvement here for quantum machine learning, and you can also kind of see how early we are with this field. Now, you could argue that obviously I've not run this on a real quantum computer just yet, but I will show you now why I haven't done this. And this is very simple. So let's just run the quantum neural network here for one data point. So let's just take test 0, theta, and now I put here simulator false. So this will call here the quantum computer. And so basically this will be the prediction for that value here. So we can actually compare this to what we get by running this on the simulator. So let me just put this here. So the simulator would tell us that it is 0.5. What is our target actually? Target is... So the target is 1. So actually this has classified it correctly, since the prediction here is bigger than 0.5, but it's only by a very small amount. So actually I think if I rerun this again, it will probably give us a different output. Yes, and indeed it does. So this is due to the finite sampling. So it means that we're just basically evaluating this here a finite number of times. So there are some fluctuations there. So actually, let's just play around with this a little bit and see if we can find another data point where the difference is a bit bigger and where the confidence is bigger. So yeah, this is actually a good data point here. So the prediction for the sixth data point from the test set is 0.2, and it indeed does correctly predict the right label. So now let's just run this on the real quantum computer and see if that is able to give the same result. So I'm just going to be executing this here. And so now if I head over to the IBM Quantum Experience, and I'm just going to refresh the page here. And so yeah, so now here I've got a program that I'm running, a quantum circuit. So now I'm just going to click on this here. And as you can see here, this is our quantum circuit. We're running it 5,000 times. And this is the circuit that we're running here. It looks a bit different than what I showed you before. I'm guessing that this is because of some swaps happening. So some qubits that are not neighbors, we need to swap around their state. So I'm guessing this is what's happening here. And so you can see that we are currently stuck in the queue, and it would take an hour for us to get our result, because there are apparently so many people using the quantum computer that it just takes us a long time to even be in the first spot of the queue. So what I'm gonna do is I'm just gonna check in an hour and see what we get and what the quantum computer predicts. All right, so now our program has finally finished its run. And you can see we were stuck in the queue for 50 minutes, and then running the circuit took 8.8 seconds. So this is in stark contrast to the simulator, where running a circuit took like a fraction of a second. So you can really clearly see that training the whole quantum neural network on the quantum computer would take ages. But the output is now a lot more promising. So now let's just go back to the Jupyter notebook and let's see what we got here. And yeah, this is really nice. we should have gotten 0.26677 from which we got from the simulator, and from the real device we got 0.2624. So it has indeed worked. So in principle you could run this on a real quantum computer, but in practice, due to this enormously long queue, we can't really do that. So you would require dedicated access to the machines, which I unfortunately don't have. So this is what it is. This is what we get. So I hope you guys enjoyed this video. I hope you learned how to code a quantum neural network. And if you made it all the way through till the end, please consider giving the video a like and subscribe for more quantum computing content.